start my video. Okay, nice to meet you, all of you. It's a pleasure to be here today. In Brazil, it's still evening, so it's not Saturday yet. So I'm in Friday, but I will talk about my work here about numerical simulation of the thermal destruction of organophosphorus. It was an undergraduate study developed here in Brazil, and it's a continuous job that we are doing here. Well, I would like to talk about combustion because combustion is an ancient way to generate energy, and it's still the most common form to generate energy. We have combustion to cook our meals, to heat our place, and the iron industry, in the automobiles industry, and all vehicles. So it's very important. Combustion, however, is one of the most important source of pollutions in the nowadays, and fossil fuels sink. So it's a great problem we should solve in the nowadays, because we will have problems associated with the climate change, pollution, and the consumption of fossil fuels. So our motivation in combustion is to study internal combustion engines and diesel engines, Otto cycle engines, new biofuels like biodiesel, bioethanol, ammonia, and alternative fuels like any methyl ester that we can burn to generate energy. Propulsion and hypergolic materials like hydrogen peroxide to send rockets to the space. We start to study security, calculation, ignition properties, and explosion parameters. Incineration, that is the main topic of this talk, and the development and improvement of kinetic models for the combustion, evaluation of rate coefficient, and rate loss. This is the long path for the combustion study. Formerly, my expertise is in ab initio calculations, but today my research group is focused in the entire side road of the combustion. Determination of creation rate, reaction rates, calculation of heat capacities, evaluation of reaction paths, obtaining chemical detail kinetic models. Now we are trying to reduce some kinetic models to employ in CFD calculation of fluid dynamics, computational fluid dynamics. So we have a large group working, investigating new fields in this entire road. We don't have any collaboration with experimentalists, so it will be a good thing in the future to have the collaboration with experimentalists. And the incineration that is the main topic for our talk. Is a process to destroy poisonous material, pathogenic material like residues of hospitals, some solid waste and liquid waste that cannot be treated conventionally by the water treatment systems, like the type of compound that we'll talk today. The incineration facility has two different kilns, a primary kiln and a secondary kiln to have almost complete combustion and destroy of entire pollutants. This type of incinerator is for solid waste material. When we put the material here, and he is separated, and his size is diminished, so he passes through the first combustion chamber and follow for the second combustion chamber. If we try to incinerate liquid waste, we should have here evaporation process to evaporate the liquid material and the gases entering the combustion chamber and be destroyed by the high temperature of the combustion chamber. The, 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 the other part of the facility is only to treat the post-combustion gases and avoid to liberate in the environment poisonous gas or some pollutant. The main idea is to release in the atmosphere only carbon dioxide and water. So by this reason, we have so big structure to treat the post-combustion gases. And the Organophosphorus family is a large group of organophosphate esters, a group containing phosphorus, carbon, and oxygen atoms. And we can add to the structure halogens, sulfur, or selenium. In some cases, we will have nitrogen groups in the structure. So according to the type of substitute, we will have the applicability of the molecule, like flame retardants, plasticizers, and whatever. And so the class is it's a large family that we can synthesize any type of organophosphorus, substitute the R group by any carbon chain, or substituting the oxygen atoms by sulfur or selenium, and the R group can be substituted by halogen atoms. And so you have the origination of several compounds of the organophosphorus family. And the usage of this family is very broad, because we can use this species as a flame retardant in foams, polymers, to avoid accidents and fire propagation, plasticizers, pesticides and insecticides like malathion, and the other phosphate here used to avoid the plagues in the agriculture. So several of these species are important for the agriculture and food production. However, some of the organophosphorus are nerve agents and were used as chemical warfare agents. A early one is the serine molecule, and a new chemical weapon is the VX agent. It have this basic structure. The VX is a family of chemical weapons, poisonous materials that some countries has his own version of VX chemical weapon. If we go back to the timeline of chemical warfare, we can go back to the First World War, when the German tests the bromchyline, and we saw the usage of chlorous gases and mustard gas in the battlefields. Further, we see the synthesis of pesticide like the G group, and so this is the timeline of chemical warfare agents, and I talk about the use of chlorous gas and mustard gas. So when the last century goes on, we see the development of pesticides, VX agents, binary weapons. So until the 19th decade, a convention for disarmament and destruction of the current arsenal of chemical weapons that we have today. So the incineration process is until now, the better way to destruct the chemical warfare agents. In our case, we are studying four organophosphorus compounds. They are the dimethyl-methylphosphonate, isopropyl methylphosphonate, trimethylphosphate, and serine molecule. They are in order here. No? Serine has a fluorine atom here, and the other species are only are phosphate esters. The chemical model that we are using to study the thermal degradation is glowed kinetic model. It was developed in the early 2000 years, 2000 two decades earlier. It is the junction of three submodels: the Varnat's model to carbon, hydrogen, and oxygen, plus the natural gas model, GREMAC 3.0, that we have the chemistry of small molecules up to 2 carbon atoms, a small model containing the iso-octane model, and the reactions, 174 reactions to describe the organophosphorus chemistry. So it's a large model, a detailed model, but it's not the best model that we have to study the thermal degradation of organophosphorus. We saw that there is some details that this model miss when we studied the organophosphorus degradation. Well, we tested 4 different fuels, because when we needed to burn organophosphorus in an incinerator, we need a fuel. So we choose to study gaseous fuels like biogas, ethane, methane, a blend of ethane and methane, and pure propane. Biogas is a blend of methane and carbon dioxide, because it's a biofuel produced in solid waste facilities. So it's a decomposition gas, a gas formed after decomposition of organic material. So it has a high percentage of carbon dioxide, and it has a high grade of sulfur compound that should be removed before the use, but is a good alternative to the natural gas, because is a fuel produced by the solid waste. And we tested this for fuels, and a large range of simulation of 800 degrees to 2000 kelvins. All calculations performed at 1 atmosphere. We simulated 2 different reactors, a big batch reactor, a well-steered reactor, and a continuous flow reactor using the Cantera 2.5 software. And with the continuous reactor, we separate 2 streams. Stream A is the organophosphorus stream. Stream B is the fuel stream. And well, this is a mistake. This stream is the C stream. It's the combustion products, CO2, pollutants, and some organophosphorus residue. And we set up the residence time in order to optimize our degradation of organophosphorus compounds. There is some details that we will discuss later in this this type of arrangement. And the first results are for the batch reactor to study the efficiency of the degradation for the organophosphoric compounds. So due to the space and time, I will show only the biogas and ethane results and the lower temperature values because temperatures higher than 1,000 Kelvin, all organophosphoric compounds are completely degraded, and below 1,000 Kelvin, we don't see the complete degradation of some organophosphorus. TMP, GIMP, DMMP are not well destroyed at temperatures below 1,000 Kelvin. And if we change the fuel biogas to ethane fuel, we'll see a better destruction of GIMP, GMP, and sarin relative the biogas. So the fuel chosen for the incinerator can affect the destruction of all compounds. And in the pollutant formed when we use biogas as fuel, we see mainly CO2, because CO2 is an input in the fuel. We see a large amount of CO2. Some reactive species, acid species containing phosphorus, and sarin produces HF. HF is a acid gas, a gaseous species that cannot be released in the atmosphere because it is poisonous. So we need to remove HF before the gas be released in the atmosphere, because it can cause accidents. The continuous flow reactor is so that the temperature and the mass flow of the organophosphorus needs to be carefully chosen, because some organophosphorus are flame retardants, and if the according to the temperature and the mass flow, it can quench the incinerator, lowering the temperature and extinguishing the flame in the incinerator. So we should evaporate, raise the temperature of the organophosphorus before enter in the combustion chamber. In other way, we will quench the reactor. And the pollutant formation when biogas is used as fuel, we can see that the sarin chemistry is different from the others organophosphorus. When we raise the temperature, the pollutants lower when sarin is destroyed, but the other compound has a peak at 100 Kelvin when we see 1,000 Kelvin, sorry, I'm saying the wrong value, 1,000 Kelvin, when we see a peak here, where is the higher molar fraction of the pollutants, but if we raise the temperature, we see the lowering of the formation of those species. We conduct a flow analysis when we can see the reaction, the most important reaction path of during the ignition of combustion. It's important to see the ignition because it is the step of the chain propagation. So we can see the species that is forming during the chain of the propagation chain of free radicals. So we saw mainly in this case the phosphorus atom flow in different molecules. This result is in the presence of biogas as fuel. The second is in the presence of ethane. We can see the difference between both schemes because the fuel influences the burn of each compound. We can see the presence of different free radicals involving phosphorus and acid phosphorus compounds, and the reaction pathways of involving the phosphorus compounds change if we change the fuel. The main result we see here is that we can alter the combustion, the thermal degradation, if we use different fuels. So the fuel is important during the thermal degradation of all organophosphorus compounds. We see several differences between ethane plus a blend of methane and ethane, relative biogas, relative propane. So each fuel participates differently in each kind of reaction mechanisms. As main conclusion, as the temperature effect in the two distinct combustion regime that we investigated, except sarin, the other organophosphorus compounds are less reactive in not prone to complete degradation at temperatures lower than 1000 Kelvin. So we need to incinerate us in temperatures higher than 1000 Kelvin to avoid the to destroy completely the organophosphorus compounds, but thermal degradation, incineration is a good method to remove organophosphorus compounds and destroy completely organophosphorus, since we have some if we take some care during the process of incineration. Different fuel blends were tested, and we see that when we change the fuel blend, we change the rate of decomposition and the concentration of pollutants during the simulation. And the main pollutants are carbon monoxide, carbon dioxide. If we have biofuel, carbon dioxide is a problem because we release a lot of carbon dioxide to the atmosphere, and carbon dioxide is a greenhouse gas, so it will cause more problem related to the temperature raise of of the atmosphere. And the three acid gases involve phosphorus. We are interested now in the thermal integration process, how we can use the released or consumed in the incineration in another process. It's our main idea now is to use the rid of incinerator for other process, not only to see the pollutants formation format. Well, thank you for your attention.